In this video, we will introduce the normal stress caused by the bending moment in a straight member. Let's imagine an undeformed straight member with an arbitrary cross-sectional area, and it is subjected to these external moments, and we know that these external moments will cause internal bending moment in the member. From common knowledge, we can predict that it will deform upwards like this. We assume the cross-sectional area stays the same, which is not true but acceptable for small deformation. If we pick a small segment on the undeformed member with a length of delta x, from common knowledge we know that after deformation, the top of this rectangle will become shorter while the bottom of this rectangle will become longer like this. But since the change in this segment is continuous, therefore, there must exist a line in this rectangle for which its length will remain unchanged after deformation, still delta x. In fact, we can extend this analysis to this entire member and realize that there will exist a neutral axis in this member for which its length will remain unchanged during deformation. Don't forget, the neutral axis extends throughout the width of this member, making it a neutral plane, like this. Using this 3D representation, let's define our 3D rectangular coordinate system. This is our x-axis, y-axis, and z-axis. And later you will know that all these three axes are centroidal axes because they all pass through the centroid point of the cross-sectional area. Before we derive the mathematical equation for bending stress, let's make several assumptions. First, we assume that the neutral plane will curve during deformation, but its length remains unchanged. Secondly, we assume that each cross-section remains perpendicular to the neutral plane. And lastly, we assume that the shape and size of the cross-section remains unchanged as well. It might help you to understand if you imagine the beam as an accordion. Here is the neutral plane that curves up during deformation, and the cross-section rotates from its original location. However, it remains straight and perpendicular to the neutral plane. Let's focus on the small segment along the undeformed beam with length of delta x as we mentioned earlier. Remember, this is our x-axis, which is the neutral axis. This is our y-axis. And at an arbitrary y position, the width of this segment is the same, delta x. After we apply the external moments, the beam curves up and the small segment becomes this. Since the blue curve is on the neutral axis, its length remains the same, still delta x. But the length of this green curve is now changed to delta s prime, which no longer equals to delta x. Since the two cross-sections have rotated from their original locations, they are no longer parallel to each other, therefore, they will eventually intercept at the point O if we extend them. And the angle they make is delta theta. Now, both delta x and delta s prime can be considered as lengths of two arcs with the central angle delta theta. For delta x, its radius of curvature is rho, and the length of the arc delta x equals to rho times the central angle delta theta. For delta s prime, its radius of curvature is rho minus y, and the length of the arc is rho minus y multiplied by delta theta. Therefore, at position y, the normal strain epsilon equals to the final length delta s prime minus the initial length delta s before deformation divided by the original length delta s before deformation. And since we know that delta s equals to delta x, therefore the normal strain at y equals to delta s prime minus delta x divided by delta x. If we substitute in delta s prime and delta x as length of arcs that we derived earlier, and cancel out delta theta, and we got the normal strain epsilon at arbitrary location y equals to negative y over rho. And the maximum normal strain happens at one of the edges which is further away from the neutral axis with a distance of c. And the absolute value of the maximum normal strain at this cross-section equals to c over rho. And for a given loading situation and for a given cross-section, this absolute maximum normal strain is a constant. Therefore, at this cross-section, the normal strain at the arbitrary location y linearly depends on its location y. This linear relation of the normal strain along the y-axis can be visualized here, with the maximum normal strain occurring at this top edge. However, according to Hooke's law, within the proportional limit, normal stress and normal strain also linearly relate to each other. Here, Young's modulus E is a material property which is a constant. Therefore, we can derive this equation showing that normal stress also follows a linear distribution along the y-axis like this, with maximum normal stress occurring at the same edge. Now the question is, what is this maximum normal stress? Let's look at a cross-section of this beam in both 3D and 2D views. This is our y-axis, and this is our z-axis according to our previous definition. Based on our previous analysis, the normal stress follows a linear distribution on this cross-sectional area like this. Now, if we pick a differential area element on this cross-section, this area is located at y location. It has an area of dA, and at y location, the normal stress is sigma y. And since we know that stress is force over area, therefore, stress times the area equals to the differential force element at this location. Now, the resultant force along the x-axis equals to the integration of dF across the cross-sectional area. Therefore, that equals to the integration of sigma y dA integrated across the cross-sectional area. And since sigma y equals to negative y over c times the absolute value of maximum normal stress, sigma max, and we can pull out the constants, the negative sigma max over c. And don't forget, the resultant force along the x direction must be 0 for equilibrium. And since sigma max and c are both non-zero, therefore, this integration term must equal to 0. And based on our knowledge of the centroid of an area, this proves that the z-axis must be the centroidal axis of this cross-section. Now, this force element dF also creates a moment about this z-axis. dmz equals to y, which is the moment arm of this force, times negative dF, which equals to this. Now, the reason why there's a negative sign here is because according to our definition of the xyz axes, a force along the positive x direction will create a clockwise rotational effect about the z-axis, therefore it will create a negative moment about the z-axis, and vice versa. Now, the integration of this differential moment element dmz across the entire cross-sectional area must equal to the internal moment at this cross-section, mz. And we substitute in sigma y and pull out the constants, and we get this right here, sigma max absolute value divided by c multiplied by an integration term, the integration of y squared dA over this entire cross-sectional area A. And this term should look familiar to you based on our previous knowledge of moment inertia of the area. This is the moment of inertia of the cross-sectional area about the z-axis, which is a constant for a specified cross-sectional area. From here, we can solve for sigma max, which equals to mzc over iz. C, again, is the maximum perpendicular distance from this z-axis. And from here, we can also derive the equation to calculate the normal stress at an arbitrary location y, and this is known as the flexure formula.